The Smart Contract IDE is the environment provided by the AstraKode Blockchain Platform to design and develop smart contracts. As both Hyperledger Fabric and Solidity rely on smart contracts, the environment is able to accommodate development of either, according to the technology choice made at project creation time. Thus, to access the environment for Hyperledger Fabric contracts, one must create a project of type contract and select such technology among the two options presented. Once this is done, the platform will redirect you to the Smart Contract IDE. Similarly to the Network Composer, to the top of the interface one can find the action bar. Here it is possible to save a project, generate it, undo or redo an action, or toggle the code preview. Furthermore, in contrast to the Network Composer, the validation toggle is embedded in the action bar for the Smart Contract IDE. The smaller action bar to the top right of the interface allows to close a project, access its settings, or share it with another user. As with the Composer, the left bar of the environment is dedicated to the definition of the global components of a contract. However, before visualizing them, it is necessary to first define at least one contract. To create a new contract, one can click on the plus button in the dedicated tab. In Hyperledger Fabric, a contract's definition modal is very simple, as it only requires the name of the contract. Once a contract is defined, the left bar will update to show all of its global components. These are the asset definitions, the custom functions, and the global data entities. If more than one contract is defined, the contract select bar will allow switching between them. I am now quickly gonna define another contract to show this possibility. It is now time to get to the core of the development effort and start defining the content of our contract. In a Fabric contract, everything revolves around assets. These are the data structures stored in the ledger, and contracts are usually built to read and write such structures. One can think of an asset as a row in a database table, the ledger. Although the ledger can in theory store multiple asset definitions, as a best practice the platform only allows for one asset to be defined for each contract. Thus, we start by defining a sample asset for this contract. To do so, we click on the plus button in the dedicated tab. This will trigger the appearance of the asset definitions modal. As with a database table, an asset definition will involve the name of the asset as well as the definition of its properties and the index to be utilized to query the asset. If one wishes, it is possible for the platform to auto-generate the CRUD functions to read and write the asset. However, as we will define this manually in the tutorial, I am going to untoggle this option. When defining an asset's properties, one can add a property by clicking on the plus button to the top right of the properties list. For our sample asset, I am first going to create an ID property of type string to act as index, as well as two sample properties, one string and one numeric. However, one can also define more complex properties if needed, as can also be seen from the type selection. Once all properties are defined, we can save them and go back to the main model. Here now, instead of the Properties button, a table with the list of defined properties will appear. It is possible to go and change them at any point in time by clicking on the Edit button of the table. Finally, we can select the ID property as query index and save the asset. As with any other global contract component, we can always go back and edit the asset definition by clicking on the three dots next to the component. It is now time to manually define our CRUD functions. To begin, we will first define the insert function. To create a function, one can click on the plus button in the dedicated tab. After naming our function, we are going to define any input parameters that it needs. One can add an input parameter by clicking on the plus button to the top right of the relevant list. Since we are inserting the asset, we are going to provide the function with all of its properties as input. These properties will then be available within the function design to be manipulated or utilize their value. Once this is done, we can save our function definition and exit its visual development environment. Here we are designing the function's algorithm by composing a flow of elements, with each element constituting in a specific action. To the bottom left of the flow visualization, one can find some controls such as zooming, centering, or locking the view. To add a new element, one can click on the plus button of the last element in the flow. Since the function is newly created, we are going to click on the plus button of the start element to get started. Once this is done, we can select the element we want to add from the list. The following elements are available: the condition element to create a condition, the data entity instantiation element to instantiate a local variable, the data entity manipulation element to manipulate the value of a local or global variable, the function call element to call another function, the ledger transaction element to transact on the ledger, the loop element to create a loop, the print element to log something, and the return element to return a value from the available data entities. To add a small degree of complexity, we are not going to insert the asset with the input properties as they are provided, but instead we will manipulate one of them and then insert the asset. To do so, we will add the data entity manipulation element. Within the data manipulation element, the primary scope property will affect which data entity is to be manipulated. After choosing our input number as primary scope, we can define a mathematical operation for it. To keep things simple, we add the number to itself by selecting it as both terms of the operation and choosing plus as operator. It is important to note that the platform handles type coercion so that only compatible data entities are selectable. Moreover, within a function scope, the only visible data entities will be the local ones, as well as any global. After defining this simple manipulation, it is time to define the ledger transaction to insert the asset. Naturally, to do so we need to add a ledger transaction component. Within the component, we must select the asset type as well as the type of transaction. In this case, we will select the asset previously defined and the insert type of transaction. Once the transaction type is selected, extra arguments will appear to map all needed properties to the ones necessary to populate the asset. Since we did not define any global or local variable outside of the function's input, the configuration for the insert becomes quite straightforward. Finally, in case we want the transaction to return a value, which in this case will be the asset that was just inserted, we can populate the return property with the name of the data entity that will encapsulate the ledger transaction's return. The insert asset function is now complete. However, we need a way to query assets from the ledger. To do so, we are going to define a query function. Contrary to the insert function, for this function we will only define one input, the index of the asset that we want to query. For this function, we first need to define the ledger transaction that will do the query. To do so, we create a ledger transaction component of type query. Within the component, we select the asset type as well as the type of transaction. Furthermore, we need to define a return name so that we can grab it to return the queried asset at the end of the function. For this type of ledger transaction, only the index is needed to be mapped to the expected transaction input. The two checkboxes at the bottom of the model can enable historical queries or lock the query result to a single value. After defining the query, we only need to return its value via the addition of a return element. Within the return element, we select the query result as primary scope in order to return it to the function's caller. We are now done with the sample contract. At any point in time, it is possible to toggle the preview for the contract's code. To do that, one must click the relevant action in the action bar at the top of the interface. The code preview showcases the code for any of the defined contracts. Within the preview, by clicking on any of the text highlighted in blue, one can access the component responsible for that part of the code. It is also possible to refresh the preview or copy its contents to the clipboard. Furthermore, the preview area size can be changed by dragging its borders. We can now generate the contract's code. To do that, one must click the relevant action in the action bar at the top of the interface. The outcome of the generation is a zipped folder containing one JS file for each contract. Moving on, the next section of the tutorial will deal with Solidity and the Smart Contract IDE in the context of developing Solidity contracts. To access the Smart Contract IDE for Solidity contracts, one must create a project of type contract and select such technology among the two options presented. Once the project creation process is complete, we are redirected to the Smart Contract IDE for Solidity. The interface is the same as for Hyperledger Fabric. However, both the contract's global elements and flow elements are different in this version of the IDE. To begin the development, we first need to define a contract. To do so, we can click on the plus button in the relevant tab. This will trigger the appearance of the contract's creation model. Next to the name, here it is possible to define whether the contract is abstract and select a function to act as a constructor. Obviously, the latter can only be done once any function for the contract has been defined. As soon as we define the contract, we can immediately see that its global elements on the left bar of the interface are slightly different from the Hyperledger Fabric version. More in detail, in addition to Fabric, here we can define events, imports, and modifiers. Moreover, since storage in Solidity works differently, there are no assets to be defined. For the purpose of this tutorial, I'm going to develop a simple contract for voting. The contract will enable its caller to cast a preference, as well as keep track of the total number of votes and of the preferences, and broadcast whenever a vote has been cast. To begin, I'm going to define the broadcasting event for the vote cast. To do so, I have to click on the plus button in the relevant tab. Within the event's creation model, I'm going to define the event's name as well as any parameters that I need to broadcast. Since broadcasting the preference will already make sense, I'm going to broadcast the voter's address. Since we need to be counting the votes, I'm going to import the established protocol to do that. However, since it increases complexity, I might still decide not to use it and implement something simpler myself. To add a new import, one has to click on the plus button in the relevant tab. Within the imports modal, I'm going to select the inheritance type, meaning that my contract will extend whatever contract I import. After that, I'm going to select the counter's contract among the provided options. This will enable any of the functions that will be defined for this contract to access any function or data entity inherited from the counter's contract. Another option for a simpler implementation could involve the definition of a global variable to count votes, to be then stored on chain. To do that, one needs to click on the plus button in the relevant tab. Within the data entity model, I will define the data entity to be of type int and be stored in storage. It is now time to create the function to cast the vote and broadcast our event. To do that, one needs to click on the plus button in the relevant tab. Next to the function's name, within the custom function model, I'm going to define the preference as input. This will be a data entity of type string, where the caller will embed their preference. Once this is done, we can save our function definition and exit its visual development environment. Here we are designing the function's algorithm by composing a flow of elements, with each element constituting in a specific action. To add a new element, one can click on the plus button of the last element in the flow. Since the function is newly created, we are going to click on the plus button of the start element to get started. In contrast to Hyperledger Fabric, here we do not have any ledger transaction element. However, there are some other elements that are unique to the Solidity version, such as the contract instantiation to instantiate a contract and the element transfer. As a first step of our flow, we're going to define a data entity manipulation element to add to the vote count. Within the elements model, we select the global vote count variable as a primary scope, and we set a math operation to have it equal to itself plus 1. As you can see, in the end I decided to go for the simpler method rather than leveraging the imported counter contract. To define a hard-coded value, one must create a data entity of type free input. In our case, the subtype will be int like the vote count variable, and the value will be 1. Unfortunately, I have just noticed that we do not yet have any means to store preferences. To remedy that, I'm going to create a global data entity of type array that can store a list of string preferences. Naturally, also this data entity needs to be stored in storage. Our next element is again going to be a data entity manipulation element. However, this time we select the global preferences array as primary scope, and we set an array operation to add the voter's preference to the array. Finally, we can broadcast the preference casting. To do that, we will leverage the cast vote event that we defined initially by emitting it through an event emission element. After selecting the correct event, we have to map a variable in the current scope to the event's expected input. To map the address of the function's caller, we can leverage the message.sender default variable. We are now done with the sample contract. At any point in time, it is possible to toggle the preview for the contract's code. To do that, one must click the relevant action in the action bar at the top of the interface. The code preview showcases the code for any of the defined contracts. Within the preview, by clicking on any of the text highlighted in blue, one can access the component responsible for that part of the code. Furthermore, the preview area size can be changed by dragging its borders. We can now generate the contract's code. To do that, one must click the relevant action in the action bar at the top of the interface. The outcome of the generation is a zipped folder with one .sol file for each contract plus some extra configuration files.